different than congruence. So that'll be the main idea to get today, is 12.4. Today is all about shapes that are similar, which is not the same as shapes that are identical. Congruent, right? That was last week. Last week we were talking about what it takes to prove two shapes are completely identical in every way. Now in 12.4, we're saying, well, what does it mean to be similar? So basically, I could just tell you off the cuff, similar shapes are the same except for size. Like one's a big version of the other. But otherwise, they're the same shape, but just one's bigger or smaller. So that's what similar means. So similar means same shape, identical shape, different sizes. So that's the general feel of it. So similar shapes are the same thing. So you might have, well, you can see it down here. See how this little triangle and this big triangle, they're really the same kind of triangle shape, aren't they? If you took the little one and you blew it up on a photocopier, it would fit right under the bigger one, huh? That's probably a better way. If you take one and shrink it down or expand it, take the little one and blow it up, or the big one and shrink it down, they would fit right onto each other, wouldn't they? So they're really identical except for size. That's what similar means. They're exactly the same, but one's just a big version of the other. Now, what does it take? I mean, we can kind of see it with our eye. We can kind of look at it and go, yeah, those look like they're similar. But how would you actually technically prove that two polygons are really similar, same except for size? Well, here's the technical definition, math definitions. Here, I'll read it for you. You know how math definitions go, right? Two polygons with the same number of vertices are similar if there is a one-to-one correspondence between the vertices of one and the vertices of the other, such that the corresponding interior angles are congruent and the corresponding sides are proportional. They're right, but that's such technical language, right? Don't read that to younger folks and expect them to grab it all perfectly, right? Let me break it down to simple language. Angles are equal and sides are proportional. That's basically the gist of what it said. Two shapes are similar if the angles are equal and the sides are proportional. Now, what does proportional mean? Like, one shape is 2 times the other, or 3 times the other, etc. So that's what we mean by proportional. One is a proportion of the other. One is double or triple or quadruple or whatever the other. So basically, if one of them has sides that are all twice as big as the other, or 3 times as big or whatever, and all their angles are equal, then we know for sure they are similar shapes. They're identical except for size. One's just a big version of the other. Otherwise, they're identical. So this is how you prove similarity for any polygon. That means any number of sides. That could be a 3-sided, what we call triangle, right? 4-sided, 5-sided, 6-sided, 7-sided, 10-sided, whatever. That's true for any number of sides. If you can show all the sides are proportional, like all the sides are double or triple or whatever, and all the angles are equal, then those two shapes are really the same shape. If you blow one up, it'll fit right on the other. Now, let's make it simpler for just triangles, because we're most interested in triangles. We want to know about all the shapes, but really triangles are the things we focus in most. So this point forward, or this section anyway, is going to be just triangles. So what does it take to show that two triangles are identical to each other? Like how do we know this triangle and this triangle are really the same exact triangle? One's just a bigger version, what we call similar. Well, all you need is 2 angles, it turns out. You don't need to know anything about the sides. It's kind of surprising. If you just know 2 angles in one triangle are the same as 2 angles in another triangle, they have got to be exactly the same shape. Everything else is just a bigger, smaller version. That's surprising. Why is that enough information? If you know 2 triangles in one triangle are the same as 2 in another, let me just make up some numbers. Numbers are always helpful. So what if I know, say, this is 50 degrees here, and this is 60 here, and this one's 50, and that one's 60. Let's say. So say we know, that left triangle, the little triangle's got a 50 and a 60. The big triangle's got a 50 and a 60, couple angles, So So it's got two equal angles. What do we know about the third angle that's missing there?
It has to be the same on both of them.
Yeah, how do you know?
Because they both have to equal width.
Because that triangle always holds 180. We get a lot of mileage out of that fact, don't we? Right? A triangle has to hold 180. So if they've got two angles the same, right? So what if 50 and 60 add up to be? 110. So how much is left? Same thing here, right? How much is left for the third angle? 70. So the third angle, this would have to be 70, and same thing there. Yeah. So if you have two angles the same, you've really got three angles the same, don't you? And if you have all three angles the same, AAA, that means it's the same exact opening at every angle. It's the same shape. It's just a big version or small version of it. Remember how we talked about earlier that AAA was not enough to prove identicalness, but it is enough, we see here, to prove similarity. It's enough to mean it's the same kind of shape, it just might not be identical because it's a big version or small version. Yeah, all right, so really all it takes is two angles. We like to say things as minimalistically as we can in math. Like, what's the least information you need to know? Well, you need to know two angles. If you know two angles in one, two angles in the other, those triangles have to be similar. Not identical, but similar. How about in part B there? So in part B, you see the two triangles we're talking about? We have this little one, and then around it is the bigger one, huh? So is the big green one and the little red one, are they similar? And how do we know? They got two of the same angles. They both got a 90, and then they both got that other angle, the E and the A, that's, it's being marked and marked, so they're telling us they're the same opening. So yeah, it's got two equal angles. Those have to be. So the big one is just a big version of the little one, right? If you blew up the little one, it would eventually fit onto the big one. They're identical except for size. All right, well, and then these are the proportions. So if two triangles are similar, then their sides are proportional. That means their fractions are equal. And we'll talk about that. That'll make more sense as we look at the homework. We'll get really specific, and I'll slow down then and show you exactly what we mean. There's two other theorems, which we'll use in a bit, for proving two triangles are similar. One of them is side, 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 and the other is side, angle, side, and we had those earlier, but they're different here. So that's why I'm making a statement down here at the bottom to help you see that difference. We had side, 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 and side, angle, side earlier, but that was for proving identicalness. Side, 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 and side, angle, side here are for similar triangles. They're proportional, not equal. In other words, read the fine print there on the contract carefully. It's a little bit different, side, side, side. It doesn't say, earlier, last week, we found if you have one triangle and you have another triangle, and you know that their three sides are all the same, that's enough to prove those triangles are fully identical, right? That was last week. That was side, side, side for proving identicalness, congruence. But now, notice the fine print for side, side, side for similarity. It says the lengths of the two triangles are proportional, not equal. See the difference? So now they're saying, okay, we're saying something like this. Like you've got a little triangle. Here, how about I do this? You got a little triangle and you got a big. And this is, 3, 4, 5, and this is 9, 12, 15. How much bigger is the big triangle than the little? How much bigger are his sides? 3 times as big. See how they're all 3 times as big? Right? If you multiply them by 3, you get the 3, 4, 5 by 3, you get the 9, 12, 15. So we're saying that proves those triangles are really exactly the same shape. Just different size. If you blew up the little one, it fit right onto the big one. Same shape. Why? Because all 3 sides in one are proportional, meaning they're, it's just triple. It's just 3 times as big, right? So in other words, if I took 9 divided by 3, if I took left side divided by left side, what would I get? What is 9 divided by 3? Well, 3. What if I took right side divided by right side? 15 over 5. 3. What if I took bottom over bottom? See, I'd get 3 all the way, wouldn't I? That's what we mean by proportional. If you take any matching sides, they call them corresponding sides. Right over right, left over left, bottom over bottom. If you match them up, you're going to get the same ratio all the way through. because the big one's 3 times. That proves that they're identical except for size. That proves they're similar when the 3 sides are proportional. And then down here, side angle side, that's the same kind of thing. It's like the other side angle side, but this one's for similarity. And again, we're talking about sides being proportional, not equal. We'll see it in the homework problems as we go. Let's dive on forward. Feel free to speak up if you want to talk more about anything. Let's start with four-sided shapes. So here's homework problem number 1. So we've got 2 rectangles, right? Those are both rectangles. And we're wanting to try to prove that the little rectangle is the same thing as the big one, just different sizes, that they're actually the same shape. If you blew up that little one, would it really fit right on the big one? Now, it kind of looks like it. I mean, it looks good, doesn't it? But how can we be, sure? What would be the technical math reasons to prove that's the case? So we got to go back and look at, this isn't triangles, right? So we can't use that triangle, side, 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 angle, angle, angle stuff. It's a four-sided shape. So remember what the rule was? Here it was, for any number of sides, not just triangles, right? What was the rule? You have to have all the angles equal, and you have to have the sides being proportional, like one shape is double or triple the other. So that's what you got to have to know for sure that they're similar when it's not a triangle. All the angles equal, the sides proportional. Well, do we have that? First off, are all the angles in the little rectangle equal to the angles in the big rectangle? Yeah, they're all 90, huh? So we got all the angles. So all the angles are 90 degrees. So yeah, all the angles are equal. Now, are the sides proportional? Like if I took the left side of the little triangle, that's 2. And then I compared that, say, to the left side of the big, did I say triangle? The left side of the little rectangle, and then the left side of the big rectangle. What's the left side of the big rectangle? 4. So the big rectangle is how much bigger? Twice as big. 4 is twice as big as 2. Now, does that work also if I do top with top? Like if I take the top of the little one and compare that with the top of the big one, is that also 2 times? It is. You check it on your calculator. $9.50 twice is $19, right? We all do money a lot, so probably that works well for you. Yeah, it is. So yes, the answer is yes. It looks like all the angles are equal and the sides are in the same ratio. They're proportional. The big one's just double. So we would, now there's 2, you know how they give us the 2 yeses and one of them's goofy? Did you already read it? Which one's the right yes? Let's try this one. Yes, the rectangles are similar because all corresponding angles are congruent. Yeah, right. And all corresponding sides are proportional. Yeah, that was great. The other yes, what does it say? Yes, the rectangles are similar because all rectangles have congruent. No, that's just crazy. Not all rectangles have congruent. That's not true. All right, so it's the first yes. That is the right reason. All the sides are equal. All the sides are proportional. The angles are equal. Let's go. We good there? All making sense? How about number 2? Which of the following are always similar? Which of the following are always similar? So first off, 2 equilateral triangles. If you have a little equilateral triangle and then you have a big equilateral triangle, are those really always the same shape? One's just a tiny version of the other. Like if you blew up the little one, would it always fit right on the big one? Or might they be different somehow?
Always the same.
Always going to be the same. How do we prove they're always going to be the same?
Because they all have to have 60 degrees.
Yeah, remember the angles in an equilateral triangle? Equilateral means all 3 sides are the same and all 3 angles are the same. And so what are the angles in an equilateral triangle? 60, because 180 total, huh? And they're all the same. That's 60, 60, 60. Yeah, so it has to have 60, 60, 60 angle, 60, 60, 60 angle. So then, remember the triangle reasons? As long as you have 2 angles in one and 2 angles in the other, we got 3 and 3. That's enough. That proves they're really the same shape, just one's bigger. So yeah, all equilateral triangles are really exactly the same shape, just bigger versions and smaller versions, huh? How about squares? Next one down here. Are 2 squares always similar? So you take a little square, and then you take a big square. Are those really the same shape? One's just a small version, one's a big version. If you blew up the little one, would it always fit right on the big one? How do we prove it? Remember what we got to do for things that are not triangles? We got to show all the angles are the same. Are all the angles the same?
Yes.
Clearly, they're all 90. Okay, but not only that, you have to show the sides are proportional. So like if this triangle is 2 by 2 and this is 6 by 6, well, yeah, 3 times as big, huh? Any square, it's gonna be proportional like that. Yes, all the sides are proportional, the angles are equal. So it's starting to seem, at this point, it could start to seem like, well, seems like everything's similar. But let's look at question C. Question C. Are 2 rectangles always similar?
No.
Yeah, well, how do we know not? Can you give me an example? What would it be like?
One side could be very long.
Yeah, kind of like that. And the other one maybe more squarish. Yeah, those two are not similar, right? If you take the little one and blow it up, it'll never fit right on the big one, huh? They're just different. They're not similar. They're not only different sizes, they're just different shapes, aren't they? They're different kinds of rectangles, aren't they? Does that make sense? So, yeah, not all rectangles are similar. Those are just totally different. Not at all similar. All right, now on part D, they try to condition it a little bit. Try to say, okay, yeah, you're right. Not all rectangles are similar. But how about if we fix it? Could we say that if you have 2 rectangles and it's a certain kind of rectangle where one side is twice as long as the other? If you just take rectangles that have one side double the other, so none of this squarish rectangle stuff, they're basically saying, right? Only rectangles where one side's double. So let's try it. So if I take a rectangle like that, maybe say this is 2 and well, let me just go 1 and 2. So there's a rectangle where one side is double the other. Now let me try grabbing a bigger one. What if I go, okay, now I'll take one like that, where this is, let's say, 3 and 6. Right? So that's 3 times as big, right? So, but again, they're saying only rectangles that have one side double the other. So one side's double the other. So are those 2 rectangles similar? Are they the same shape? Except for if you took the little one and blew it up, would it fit right on the big one? Yeah, it would, huh? How do we prove it? Remember, for shapes that are not triangles, what do you got to do to prove they're really similar? All the angles have to be equal, and they're all 90, and sides proportional. Yeah, it's triple. Right? So yeah, so if you only limit yourself to rectangles that have one side double the other, yeah, all those are really the same shape, just bigger and smaller versions. But not all rectangles in general, as we saw in part C, huh? Those can be different shapes. Making sense? The idea of similarity versus identicalness? All right, let's hone in now. This is number 3. Let's hone in on triangles. So we're going to do a whole bunch of triangle questions. These will be pretty easy for you, I think. We want to prove those 2 triangles are actually similar. Same shape, one's just a bigger version. So on. This is 3, part 1. So what do you think? Are these 2 similar? And if so, why? How could we prove it? What were the ways we proved? The main thing we look for is the double angle. Remember the AA? And it's right there obvious for us, huh? Yeah, they have 2 angles the same, right? This 37 degrees is the same as that 37, and this 74 is the same as that 74. So they have 2 equal angles in the 2 triangles. So yeah, that proves they're similar, doesn't it? That's all it takes. It's really easy for triangles. If you can just show they have 2 angles the same, then they're similar. So where is down here? It's part C. So yes, the 2 triangles are similar by AA, angle. We always look for that first. Now, they ask for the scale factor. You know what they mean by scale? Sometimes like if you build a little model airplane or a model car, they'll say this is 1/10 the size of the original, or 1/32 the size of the original. So that's what we're talking about here. The little triangle is they're saying triangle ABC over triangle DEF. That's what they're saying. The scale factor of ABC to DEF. That means a fraction, doesn't it? That means a ratio. Like, again, if you build a model plane or car, it'll say this is 1/32 the size of the original. It'll give you a fraction. So what is it for these triangles? What is the scale factor? Well, all you got to do is grab one side and compare it to the other. It's just 2/7. The little triangle is 2/7 as big as the bigger triangle. It's 2/7 of the bigger triangle. So I just see what I did. I just grabbed the side on the ABC triangle divided by the side on the DEF triangle. But they have to be corresponding sides, bottom with bottom, that match up. So that's good. We did it. 2/7. That's the answer they want there. The little one is 2/7 of the big one. Doesn't really look like it, does it? Looks like it's almost as big as the big one. But anyway, we'll just do that. They say the figures are not drawn to scale. All right. We good there? Questions? Try number 2. How about those two triangles? Can we prove those two triangles? The one on the left, the one on the right, it's kind of turned upside down. Are those similar? And why?
Because AA and one side.
Yeah. Yeah, we have, whoop, I bumped the thing. We have AA, don't we? They both have a 90, and then they both have this angle. So they got two angles. So by AA, yes, there's down here on D, yes, they're similar by AA. All you got to have two angles of one, two angles of the other. Now, what about the scale factor? So triangle, they want me to go triangle ABC over triangle EDA. Right? ABC, this one, over EDA, that one, right? EDA is the one on the right. So what should I grab? Should I grab the 6 with the 12? Yeah, you could do that. Or you could grab the 1 with the 2. Either way, if you reduce the 6/12, divide by 6 top and bottom, you're going to get the same answer, aren't you? The scale factor is half. The little one's half as big as the big one, huh? That's what we're saying. So you see how you have options for the sides? They give me a couple of sides. It doesn't matter. But you do have to grab corresponding ones. Do you see what I did there? The 6 matches with the 12, doesn't it? Or the 1 goes with the 2. So as long as you grab corresponding, it's all good. Reduce the fraction. Half the little triangles, half the big triangle. All right. I'll keep moving unless you got more to add. How about part 3 here of number 3, part 3? The little triangle inside, this one in here, and the big one around it. Are those similar triangles? And if so, why? What do you think? Are those similar triangles?
Yes.
How do we know?
Is they two of the same angles?
Yeah, what I see this angle is the same as that angle. Their upper rights are the same. What's the other one?
They share.
Yeah, they share right here, angle A, right? The front left piece there. Let me get rid of all my extra marks here. Yeah, they share this angle right here. That's the left front for both triangles. That's the left of the big one. That's the left of the small one. So obviously it's the same as itself. So they both have that angle the same, and then they have the other angle the same. So yeah, they got two angles. So it's again, angle, angle. Now, this one's a little more tricky on ratio. How about I give you a chance to think about it? They're saying triangle ACD. So set up the fraction. ACD to triangle ABE. ACD to ABE. Can you...
You're right. It just
12? Yeah, right? Because this right here, this is the top of the big triangle. And so what is the top of the big triangle? How long is that? That's got to be 12, doesn't it? That's 9 plus 3, 12, right? Because of the length of 9 and the length of 3 added together. So the top of the big triangle, and then the big one's on the top, the ACD. See how they go A, C, D? They're starting with the big one on the top here. So that's 12. And then on the bottom, they want me to put the small one. So what's the top of the small one. That's just a 9, huh? 12 to 9. Now, I got to reduce that, but that's it at first, and then we just reduce that fraction. 3 goes into both those, right? So that would be 4/3. So the scale factor is 4/3, meaning the big one is 4/3 of the little one. Another way you could say that, they want you to leave it as 4/3, but do you know how to say 4/3 as a mixed number? Might be more meaningful that way. The answer is 4/3. We don't want to answer differently, but yeah, do you remember mixed number? That's the same as 1 1/3, huh? So again, we're going to put in the answer as 4/3, but it maybe means more to us to say the big one is 1 1/3 of the little one. That's what it is. That's what we're really saying when we're saying it's 4/3. It's all of the little one and a third more is what it is. It's a third bigger. Good with all that? The scale factor? All right. Now this one's a little more tricky. Part 4. We're still on question 3. This is part 4 now. Are those two triangles similar? Are they the same shape? One's just a bigger version.
Yes.
How do we know?
Side angle side.
Yeah. First off, what angle do we know they have the same?
B.
Yeah, so this one and this one have to be the same. Why? Why are those necessarily equal? How do we know right away that this angle equals that angle?
Because of the lines.
Yeah, diagonal, right? Diagonal angles. Anybody remember the technical name? They're not, I always call them diagonal angles. I think that's a better name, but
Adjacent.
geometry has a word. What is it?
Adjacent.
Not adjacent.
Vertical.
Go through the list there. Yeah, vertical. That's the one. Yeah, I don't know. I always think vertical is straight up and down, but whatever. They named it, not me. So they're called vertical angles. They're just diagonal. So diagonal angles are always equal, right? In all shapes, all times. So yeah, those are vertical angles, diagonal angles. They're equal. So yeah, and then you said side angle side, Kindle. So now, that's right, isn't it? We got this side and this side and this side and this side and an angle in between. So that's side, angle, side. Now, this is not the same as what we did last week, side, angle, side, for proving two triangles are identical. So here we see the kind of really bear it out. What do they mean by it's a different kind of side, angle, side? Here we are. So last week we proved, if you had two triangles, if you had two triangles like this last week and we knew they had this angle and this was like 7 and 10 and this was 7 and 10, then that would mean they're totally identical, right? Because if you have two sides, they both have a 7, they both have a 10, and they have the same angle in between, everything's equal, those would be identical triangles. That's side angle side last week, proving identicalness. Now, we're not talking about identicalness. This triangle is certainly not identical. It's smaller. No way they're identical. But is it similar? So for similar, you don't have to have the sides equal. You have to have them proportional, meaning same fraction. So what we have to check is not are the sides equal, but are they in the same fraction? Well, how do we do that? What fraction exactly? Well, you have to make sure you're matching up corresponding sides. So let's start with the 2 here. In the left triangle, that 2 plays the same role as what number? Let me get rid of all this stuff. What number in the bigger triangle? The 3 or the 7.5? How do we know which one he matches up with? It's the 3. Why? How do you know it's the 3, not this? How do you know the 2 goes with the 3? They play the same role in their triangles. How do we know? Yeah, it's smaller, bigger, right? You said the 2 is, in his triangle, he's smaller than the 5. He's the smaller side. Just like the 3 is the smaller guy in his triangle. Do you see that? The 2 plays the same role as the 3. He's the small side in his triangle, right? In the little triangle, 2 is smaller than 5. In the big triangle, 3 is smaller than 7.5. So the 2 and the 3 are corresponding, we call it. That's the technical word that they put in that first definition. Corresponding sides, meaning sides that play the same role, sides that match up. So yeah, the 2 and the 3, so you could set up a ratio 2 over 3. That's the ratio, that's the proportion between the little triangle and the big, the corresponding, the matching sides. That's got to be the same, if they really are similar, that's got to be the same as 5 over 7.5. So the question is, are those fractions equal? That's what we're trying to answer. You see what I'm setting up? I did 2 with the 3 and the 5 with the 7.5. Now, do you guys have your calculators? What is 2 divided by 3 on your calculator? We're going to see if these fractions are equal by changing them to decimals. It is 0.6666 forever, right?
Yeah.
And what is 5 divided by 7.5? So they do have the same fractions. They are proportional. So yes, those are similar triangles. Does that make sense how we proved that? They're in the same ratio. That left triangle is 2/3 as big as the right one. His top is 2/3 as big as the 2 is to the 3, and the 5 is to the 7.5. Now, so our answer is then down here, side angle side, and the ratio 2 to 3, right? The ABE is the one on the left, triangle ABE over triangle DBC, 2 over 3. Or you could put 5 over 7, but they don't want that answer because they want a simplified fraction. So let's just give them 2 over 3. Is that good? That makes sense how we proved that one? All right, so that is it finally for that question. That was number 3. It was a whopper. On to number 4. All right, so in question number 4, now we're going to start to actually solve for pieces of triangles. So in question number 4, let me just go to a bigger version of it. There it is. So there's part A. So here's question number 4, part A, the upper left-hand corner there. So they want us to find that X. See X up there? So we want to find how long is that little piece X. Those two triangles are similar, they're telling us. Where are they saying that? Right there. See that little squiggle? That means similar. Remember the word for congruent, we have equal with the squiggle. That means congruent. That means identical, right? That was last week. The equal sign with the squiggle. That means those are completely identical. Now, I think, is it called a tilde? It's got a formal name. I think it might be. Anyway, whatever. The little squiggle thing. That means similar. It means they're the same shape, but one's a bigger version. So they're telling us, hey, this little one in the top, it's exactly the same as the whole big one. They're really the same. If you take the little one and blow it up, it'll fit right on the big one. It's really the same, except for size. Okay, so great. So what does that mean then about X? How do we solve for X? What are we going to do? We need, if the little one is similar to the big one, if they're similar, that means the ratio of their sides will be equal, will be proportional. Same fraction, right? So here's how we could do it. We could do the left, let's go left over right. How about that? I'm going to go left over right, and I'm going to do it for the small triangle, and then I'm going to do it for the big triangle. So there's all kinds of ways to do this, but I'll just show you one way. So I'm going to go left to right, and then left to right. So what's the left side of the small triangle? Well, it's that 3, huh? Good so far? And what's the right side of the small triangle? It's just X. We good? And then what's the left side of the big triangle? Yeah, all of this, huh? What is it? 6, right? Because it's 3 plus 3, 6. Right? Because one piece is 3, the other piece is 3, so the whole length is 6 there. Does that make sense? So I'm doing left to right, little triangle, left to right, big triangle. They have to be equal. That's because they told us these triangles are similar, so that means the ratios of their sides, their corresponding sides, have to be the same. So left to right for the little triangle, 3 over X, has got to equal left to right for the big triangle. So the big triangle, his left is 6. And what's the right for the big triangle? This is 6. That's the left for the big triangle. Now, what's the right for the big triangle?
7 plus x.
Yeah, x plus 7 or 7 plus x, either way. Does everybody see that? It's the whole x plus 7, isn't it? Because x is the top part, 7 is the bottom part, so the whole right side is those added together. X plus 7. Is that good? It's a common mistake I've seen many times over the years that students will, they'll think that you can just go 3 over x and then 3 over 7. Do you see that? That actually won't work. Do you see what they're doing there? I just seen that a lot over the years. Let me clean this up and show you. Don't make that mistake. I've seen students go, I'll just go 3 to x, 3 to 7. Just like that. 3 to x, 3 to 7, and just solve that. We're not done yet. We're going to cross multiply and solve rights. But let me just tell you right now, that ratio won't work. Why not? What's wrong with that? Let me right now help you with that. Do you see that 7 is not a side of any triangle? It's part of the big one, but it's not a whole side of the big one or the small one, right? 7 goes from there to there, doesn't it? So 7 is part of the big one, but it's not the whole right side of the big one. It's not the whole right side of the little one. It's not a side of any triangle. So that won't work. So don't just look at it and do it. Make sure you're taking whole sides of the triangles, and then you'll be good. As long as you're dealing with whole sides, you'll be safe. And there's a lot of other ways that are right. There's a ton of other ways to set this up that are also correct. Maybe I'll show you one in a minute, but let's just finish with this one. But that one would not be okay because that 7 is not actually a side of the triangle, is it? See that? All right, so we have to make sure we're taking sides, and then it's all good. So we did left side to right side for the little, 3 to x, and left side of the whole thing, 6, and right side of the whole thing, x plus 7. So that's good. So let's solve it. Now, remember how to solve two equal fractions for Math 10a? Diagonal, diagonal. Cross multiply, diagonal, diagonal. So 3 times x plus 7 and 6 times x. Good there. I just went diagonal down. Let me scoot that over so it's not right next to that 7. So again, I went 3 x plus 7, 6x. So I just went diagonal and diagonal and just lay them all flat like that. And then what do we do on the left side? Remember your algebra? A little bit. A little distribution there. 3x plus 21 equals 6x. We good to there? Now we're trying to solve for x, huh? Right, remember the equal signs like I separating well x. We're saying I want to be alone. So what do we do to get x alone here?
Subtract 3x.
Yeah, subtract. Remember when you have x's on both sides, you get rid of one of them? Yeah, so subtract 3x from both sides. Boom. Like that. Now what do we do to finish getting x alone? Divide by the 3. Divide by the 3. And that's 7. X is 7. And we got it. Yeah.
So I have a quick question.
Cammy,
Kind
yeah.
of a little off topic, but just for my own curiosity.
Other right ways. Like some people, like I did left to right. That's fine. But some people prefer to do it like this, and it's totally right and good. As long as you're taking sides, whole sides, right? Some people go, well, I'm going to go 3, the left side of the little to the whole left side. 3 to 6. I'm going to go small to big. Some people like to go, I'll just do the small triangle to the big, 3 to 6, and that's got to equal small to big on the right side. What's the small? X. And what's the big? The whole thing, x plus 7. That will work as well, because we're taking whole sides, and it's just as corresponding. You can see it's the same. Look at the very first step. If I go cross multiply, what am I going to get? 3x plus 7 and 6x. See how that's the same equation we had right there? It'll work. So there's all kinds of right ways, as long as you're taking whole sides, it's all good. It'll work out. Let's try one more before we run out of time here. Here's part B. Can you solve for x in that situation? Here's the x. They're telling us right here that these triangles are similar. So the main thing is you gotta find out who x matches up with in the bigger triangle on the right. Who plays the same role in the triangle on the right that x plays in his triangle? Who corresponds with him?
2 and 5.
You got to look at the angle marks, right? That's probably the best way to tell. See, the x is the one sitting between the single and the double. So who sits between the single and the double in the other triangle? The 9. So the x goes with the 9, right? And then pick your only other option is you got to use that, the 2 and the 5, huh? 2 and 5. Does that make sense? Now, a good question I often get is some people think, well, how do you know if it's 2 and 5 or 5 and 2? Like, how do you know which way it is? Well, it would have to be 2 and 5 the way I did it, because that would be consistent with what I started to do. What do I mean what I started to do? What I mean is, I started with the triangle on the left, right? This is the triangle on, this is the triangle on the left, this is the triangle on the right. I started with the left and then went to the right. You could go the other way. It doesn't really matter. But I started left to right, so that means I've got to go left to right on the other one, so I'd have to be 2 to 5, because that's the left and then the right. Now, you could do it the other way. You could have started from the beginning with 9 over x. That would have been fine. But if you do, you're starting with the right triangle and going to, then you're doing right over left. So then just make sure you do right over left for the other one, 5 over 2 for the other one. And it'll all be good. As long as you're consistent, left, right, or right, left, it's all good. And then how would we finish solving either one of these? We just cross multiply, right? Diagonal, diagonal. 5 times x is 2 times 9. 5x is 18. Last step. Divide by 5. Remember all that? And there's the answer they want. 18/5.